what is in the water in Freiburg? Look at sort of the recent technical innovations being driven there.
Some of the people from the Berlin team came to Freiburg. They're like, whoa, this is actually really nice here.
Professor Frank Hutter is building the ChatGPT for your spreadsheet. Prior Labs, his company, have launched TabPFN, a world-leading foundation model built on tabular data, the data we use every day from Excel through to relational databases. In this episode, we talk about Frank's experience going from academia to launching a startup, how he's scaling engineering from Freiburg to take over the world, and how tabular foundation models can achieve a lot more than just predictions. I'm James Wise, and this is What's Next? Conversations with founders building the future. Frank, thank you so much for joining us at What's Next.
It's awesome to be here.
So look, you've been traveling a lot recently, covering the world, talking about the breakthroughs that Prior Labs have had with their tabular foundation models. So today we really wanted to dig into what you're building and your incredible background, both sort of academic and as a builder. Before we do any of that, can we talk about where we are today? What is Prior Labs doing, and where is TabPFN, your foundational model, in terms of its capabilities?
Yeah, I mean, TabPFN is really trying to revolutionize tabular data, predictions on tabular data. So tabular data is this field that just hasn't been revolutionized by deep learning yet, very much in contrast to language, to vision, etc. Tables, like all the forecasts that are being done, the technology that's being used is really stuck in the 2000s. It's gradient boosting methods that have been developed back then. And there's this huge industry that's been built over the last 50, 60 years that runs on tabular data. And very much in contrast to LLMs, well, this industry is there and it just is waiting to be revolutionized. And so it doesn't need to be built. The better methods need to be plugged in and a lot of value will follow. So that is what we're tackling right now with TabPFN. In January, we had a Nature paper introducing TabPFN v2. V1 was sort of 2 years earlier, sort of an early version that showed some promise, but V2 was really the first practical data science solution, but for small to medium data sets, so up to 10,000 data points. And in the meantime, a month ago, we released TabPFN 2.5 that scales up to 100,000 data points and is state of the art there. And last week, we also released scaling mode that now completely drops at size limit. And yeah, we've benchmarked up to 10 million data points and are super excited to now basically tackle any type of data.
So you're this new type of foundation model for tabular data, which, as you say, in the last year has scaled, many magnitudes, which has been incredible to see from an investment perspective. Can you talk a little bit then about the types of use cases that people listening to this may want to use TabPFN for, or tabular foundation models generally?
Mm-hmm. Yeah, I mean, there's really, tabular data is everywhere. Basically think of Excel spreadsheets, relational databases, time series forecasting. There's demand forecasting. There's the financial market. There's a medical market. There's industrial. So predictive maintenance, there's in the medical market, for example, omics data. Well, what people can do now, basically take your blood and then predict, do you have early stage Alzheimer's or not? Stuff like that you need to have patient cohorts. And actually, TabPFN can get away with half the data than other methods to get the same performance. And if you only have to have half the patient cohorts, then you can save many millions on any medical study, for example. So that's in the medical field. But then, of course, in the tech industry, any type of pricing, any type of in insurance, for example, lending, or customer churn prediction, there's a lot of value in all of these. And each single use case basically is many millions of dollars that we could actually help a single company save, and sometimes in the billions. And this is it's such a horizontal field that it's incredible that the value that we could generate for society and also help just make better decisions, more rational decisions, and make less stupid decisions.
I'm in favor of less stupid decisions. Because it feels counterintuitive, technically, that the world is running on tabular data, as you say, right? Whether it's spreadsheets, whether it's databases, relational databases, that was the way the world was running. And a lot of machine learning was built on top of tabular data historically. And then 3 or 4 years ago, it was actually natural language, which saw this breakthrough in capabilities thanks to the transformer models and applications like GPT and Gemini models. And in a way, tabular data, which, financial industry, as you say, healthcare industry, everyone relies on, got a bit left behind. Why did that happen? Why was it there's such a step change in natural language through these GPT models before we've seen it in tabular data?
Yeah, it's a great question. And it's just historically, tabular data has been very hard for deep learning methods. So in tabular data, you typically have these fairly high-level features that are generated by humans. So for example, a patient's blood values or a person's bank account or their income. These are really high-level features. In contrast to, for example, language, it's a single word, or in images, a single pixel carries almost no information. And you need deep learning in order to actually learn these successively abstract layers of features. So that's really where deep learning started, is in computer vision, to basically replace these feature cascades where you first learn little edge detectors and then you learn contours and you learn to combine the contours to little image pieces, and those image pieces in the end you maybe have a linear classifier. But in tabular data, you're already at that top. You don't need to have these features, and you just are given them. And that didn't need to be revolutionized by deep learning. So that's why deep learning first focused on images and text, where you actually really need to have this. And deep learning has tried to actually revolutionize tabular data before. So there's been many claims for the last 10 years. Oh, here's a new deep learning that's great on tabular data, benchmarked on one data set and giving reasonable results. And then you benchmark it and it's just horrible in all the other cases, because there is such a diversity in tabular data. There is heterogeneous data, there is categorical features, there's continuous features like numerical values, there's missing values, lots and lots of them, there's outliers, there's imbalanced data, there's all these complexities of real world data science that you don't have in images. It's a pixel, pixels are pixels, and you can just not worry about all these oddities. And that's why deep learning has tended to actually fail for tabular data. And what is now different is we actually don't just feed a single data point to our neural network, but we feed the entire data set to the neural network. Very much like in a language model, we feed it in the context. So you can think of it as like features for data point 1, and then target of data point 1, features of data point 2, target of data point 2, all the way to maybe 1,000 or 10,000 or 10 million. And then ask the model to make new predictions. And that allows the model, including a transformer architecture, to actually learn the relationships between the data points and actually make good predictions. And basically, this TabPFN is a transformer that has been pre-trained over hundreds of millions of these data sets. In contrast, a normal neural network would just take your one data set and learn on that, and you run gradient descent on that data set, and that's slow and it overfits. And that's precisely what data scientists hate. You want to be fast and you don't want to overfit, and that's where tree-based methods, etc., have shone in the past. But that's where actually with TabPFN, you're even faster because you have pre-trained to do this. So you just need to do a forward pass through a neural network. Just with ChatGPT, you don't train it anymore. You pass your data in your context, do a forward pass, and you're done. There's no graded updates anymore of the model, and that is the same with TabPFN. So, and it has learned not to overfit. So if you have a small data set, then it has learned to look at the test data set, at the loss of the test set, and get good values there, and in particular get good cross-entropy losses there. So be well-calibrated, make predictions that are correct. And if they're incorrect, then at least TabPFN should say, for this data point, I'm actually not very sure. So you never want to make a prediction and be sure about it and wrong, because then that's really bad for the downstream decision making, right? And this type of overfitting, that happens a lot with normal neural nets. But if you actually learn across hundreds of millions of data sets for these data sets that you train on, you can look at the test set and can learn to actually not overfit on the test set. And then for a new data set, you just make predictions that are not overfit.
Yeah. And so the difference in the experience of being a machine learning or data scientist today when using TabPFN is pretty magical. It's a bit like the first use of ChatGPT, right? Because beforehand, when it came to natural language, maybe a few years ago, everyone built their own little models or borrowed some open source model maybe to fix some holes in their chatbot. And now you don't need to build your own, because out of the box, the GPT or Gemini series or whatever is pretty good. Today, there's millions, and perhaps we're in the billions of individual models built on tabular data, whether it's linear regression, in different techniques, right, by data scientists out there. Is it your view then, and the vision of TabPFN, that hopefully a lot of those very bespoke models will be able to be thrown out, and you'll just be able to plug in TabPFN and have these almost, as good, if not better, predictions made?
Yes, absolutely. So we indeed already have customers that replace dozens and hundreds of different models with a single model, TabPFN. And that is precisely what we want, right? It's you just feed all your data in the context, make a prediction, and that makes it so much easier to serve, makes it so much easier to handle, and so much easier also to teach your the folks using it. Then having all these bespoke models, and the data changes, and the model is it was built by this intern a year ago, and nobody knows anything about it anymore. Yeah, that goes stale. And with TabPFN, it just put the new model, put the new data into the context, do a prediction, works directly out of the box.
Yeah,
and also in contrast to the previous workflow, given a new data set, you would basically have this data science workflow where a data scientist goes, plays with the data, tries some different models, like maybe a cut boost, an XG boost, maybe some support vector machines or random forests, some extra trees, linear models, all kinds of different types of models. And then also tunes the hyperparameters of all these models. And it's very slow of a workflow. Can take, depending on how good the data scientist is, maybe at least hours, but sometimes it takes months. And with TabPFN, you just take the data, put it into the model, and make predictions. And basically, while you write the next line of code, you already have predictions that would tell you, oh, here's an outlier, etc. And that is the power of foundation models, and we're bringing that to Tabular. Yeah.
It's amazing, and it's so counterintuitive that this works. As someone who doesn't have a data scientist background, when I read your paper before it came out in Nature, and just as we were investing, the fact that synthetic data sets trained in the way that you do train your models can help someone predict the next outcome, whether it be a price change or the risk of an insurance claim, or indeed healthcare diagnosis, all using one model, is kind of astonishing. Can you talk to us a little bit about your career and how you've ended up, being, at the very frontier of probably one of the biggest changes in data science today?
Yeah, so I've been a professor, actually, at the University of Freiburg, and before that I was a postdoc at the University of British Columbia, and PhD student there. And sort of in these 20 years, I've always worked on automated algorithm design, always making algorithm design simpler and more direct, less manual. And then also started this area of AutoML, automated machine learning. I ran 8 years of workshops on that. And then we transitioned over to a conference that is now in its 5th year. Built up this really successful branch of machine learning that is all about democratizing machine learning, making it less manual, taking away all this manual selection of different models, these hyperparameter tuning, finding the right neural architecture of neural networks, that is so manual in a lot of current workflows, and we were trying to get past that. And AutoML also was applied for tabular data. We built this AutoSQLearn, for example, which wraps around scikit-learn, which is the most popular traditional machine learning platform, and has won competitions already back in 2015 against teams of data scientists. So there's a long history there. But AutoML was always this slow thing that tried a whole lot of different methods, tried a lot of different hyperparameters. The data scientist didn't have to do that anymore. The machine did it, but it was still slow and very tedious. And we worked a lot on speed up techniques, like trying like smaller chunks of the data and trying less epochs and so on, in order to be faster and faster to get to the point that the data scientist would get to, and go further than that. But it was still something that, this would never run in a second. It's typically and it was perceived by the data science community as, if you don't want to continue further, then you do AutoML. Then you run it over the weekend, you get some epsilon improvement, and then you end right there. With TabPFN, in contrast, you could just run this within seconds and then actually iterate on the data, iterate on your feature engineering. That's where data scientists are really excellent in, is to have all these great intuitions about data and what different features might actually work, which oddities in the data might be there, whether there might be leakage and so on. And like, you want to have this interactive workflow, and you can have that with tabular foundation models, and that's something where AutoML didn't actually really work.
Because, as you say, for the last 20 years, but certainly for the last decade, the work you've been doing has transformed the lives of data scientists, the working lives of data scientists. There isn't a data scientist or a data engineer who doesn't know who you are from your previous work. And I'm sure they're very grateful for everything you did with AutoML. But all of that, my understanding was predominantly in an academic context, right? You were a researcher and an academic. So what changed in the last year that gave you the confidence to say, now's the time actually to leave academia and go into building a business around this new innovation of tabular foundation models?
Yeah, very, very much so. All of the success was in the academic world, and we basically built great systems for our friends who are also academics.
Yeah.
And they weren't used as much in the real world, in the industries and so on. And I very much felt like, okay, this is sort of as far as I can go in academia, and in order to achieve more, we need to actually build really great products that improve upon what we did before. At the university, I did at some point, like at the peak, have 6 research engineers, which is super hard to get funding for at the university, and it's really hard to get the best people want to work at a university where industry pays much higher salaries to great engineers. Nevertheless, we built great systems, but they weren't as great as the systems that we can build now. Now we can really, it really feels like we're being unleashed, and we can now bring this to the real world and to industries. And we can iterate so much faster than we could iterate before. I mean, you see the progress of
That's
like a 1,000-fold scaling in 1 year. So I'm super excited about that.
How did you go about finding that founding team? Can you talk to us? There's 3 founders of Prior Labs. Can you talk to us a little bit about how that got going?
Yeah, so Noah already was working with me on TabPFN. He is the first author. He was like really ingenious, and in actually writing the papers and in writing the Nature paper, I sort of had to hold him back a little bit and say, like, no, we have to do this like really academically so that the paper gets in and so on, with his mindset. But he always wanted to, like, he always had this founder spirit, like, let's move, let's get going, try this. And when we finally, then founded and had the Nature paper done, it felt like, he was completely unleashed and just working so hard and so efficiently. And so I was super excited about working with him. But I like I personally have like zero expertise in running a business. Noah had like at least some internships with Boston Consulting, etc. But we clearly needed someone who knows how this world of business runs, and we're actually looking for a co-founder. And Noah found Storage, and we talked to a bunch of different people before, but with Storage it just really clicked on a personal level, and he had this great background in both finance and VC, and we knew that there's tons and tons of applications in finance, and we needed someone who knows how the VC world works. And we started working together, so started dating for a little while and see how it went, and it went great, and we're like, okay, let's do this.
You decided to get married, as it were, in the startup context. And after you'd come together as a founding team, obviously you raised money pretty quickly. It was a pretty fast process. We were fortunate to know of you, obviously by reputation, and come across you relatively early. What was your experience of fundraising for the first time, and how did you come to make a decision of who to work with?
Yeah, actually, well, it was the first time, but I really liked the process. We fundraised for about a month, so it was really fast. And kind of went from when we were looking sort of 6 months earlier, not really knowing anything, talking to some people. We didn't really get a lot of conviction from people. They didn't see the product behind. And then by the time we were fundraising, we were ready, and we had the product vision. And then it was just once we got conviction from some VCs, and it spread like wildfire. And fortunately, Balderton heard about us. And I loved the journey. I remember we were here in actually this room, talking to you, and I felt the energy and felt like the conviction from your side, and felt you share our vision, and the rest is history. It was great working with you so far, and I very much hope that we will continue working a lot more in the future. And like the help we've got from Balderton in terms of talent and guidance, and just in general help in navigating how founder life should be, and like whom we should hire, whom we shouldn't hire, how we need to deal with everything is it's just super useful.
And you're based in Freiburg still. The team are based in Berlin. You're opening up internationally as we speak. How have you found that balance of still being in Freiburg? And what is in the water in Freiburg? If you look at sort of the recent technical innovations being driven there, I think there's two companies in different fields between Black Forest Labs and yourselves that are building world-leading foundational models from a town which, while beautiful, is relatively small.
Yeah, it is relatively small, but it has really world-leading researchers. So I'm at the university. I'm not the only professor. There's also other professors that are extremely strong in computer vision and robotics, in reinforcement learning, and just general machine learning. And there's really great talent over the last decade. There's been the teaching has been really excellent, and the master students are excellent, and then the PhD students are excellent, and then there's great people and great talent you can hire, and then also great talent that actually goes and founds. And so that is clearly something that is great in Freiburg. It's also a really beautiful place. I mean, our team is sort of split half-half, Freiburg, Berlin. Research is a bit more in Freiburg. Engineering is a bit more in Berlin. And now we're, of course, also opening in the States. But when actually some of the people from the Berlin team came to Freiburg, they're like, whoa, this is actually really nice here. and so you can actually attract really strong talent when they finally learn about what Freiburg is.
Yeah. Well, it's amazing. And look, I obviously spent time in Oxford, and we've invested in companies in there. And, Freiburg's small even compared to Oxford, but it has this incredible density of intellect. And I always think about, San Francisco, the parts of San Francisco where, it's Palo Alto or the Mission, where there's lots of people building companies, are very, very small. And you get this bizarre serendipity where you can literally bump into someone in the coffee shops, because there aren't that many of them, who's working on a novel thing which is actually really relevant to you. In cities the size of London, as much as we try to bring everyone together in the Balderton offices, and we try hard, they're so vast. It's great because you can meet people from, fintech or marketing, or you can meet someone in the civil service, or you meet someone in the arts. That's great, but you don't meet many other people in tech just because it's so vast. Whereas you have that intensity in Freiburg, actually, which is a pleasure to be around.
Yeah, and then we'll actually meet people not just in the coffee shops, but actually on our terrace, because we're moving to the same building that like Forest Labs is moving to. It's going to be, it's the best office building in Freiburg, and it's going to be really nice.
Yeah. No, I think it's an amazing place to be building a company. But as you say, while Freiburg's great and Berlin's great, you have built and launched the most successful tabular foundation model in the world, and obviously you want it to continue to be that way. How do you think about attracting global engineering talent, and what do you have to do to win over engineers working in this particular field today to make sure that you remain this sort of absolute shining light of excellence when it comes to tabular data?
Yeah, so many of the engineers we speak to are actually drawn to the fact that we have a world-leading foundation model. So it's already the existence of what we have. Then, like anyone that looks at our papers and so on, they see, look, these guys here had 19 papers at yours, and that is something that not a whole lot of other people can say. And the engineers, while they excel at writing code and so on, they're of course also looking at, okay, what is this company that I'm getting into? Do they have like zero credibility in terms of papers and so on, or do they have this background of people like our advisory board and our founding members, Bernhard Schölkopf, he is the #1 in the world in causality, Causal ML, and that's precisely what we're building on. And my background in AutoML and tabular foundation models, there's that attracts a lot of talent. But then, of course, also Noah is this great technical leader and is really building amazing technology around this, an amazing product, and that's also what people are looking at, and the potential impact that you can have, because this is now the field that is up and coming. You can, of course, stay in LLMs and maybe go downhill with them, or join the next big thing.
Yeah, and we're seeing this rise of novel foundation models. Tabular data being a great example, but voice with companies like 11 Labs and others, embodied AI with companies like Wave leading in that space. And so, what I'm hoping is we see all these different modalities develop and continue to develop. They require different types of engineering excellence, and they have different use cases. But I imagine in a few years' time, we won't just be talking about LLMs. We'll be talking about the intersection of them all. How do you think then about the future of tabular data and tabular foundation models and what they can do and just how far they can go? Because there's some pretty wild claims out there about the underlying nature of science in some ways, but lots of other industries being tabular. And so perhaps your type of technology should be applied to a much broader range of fields.
Yeah, I fully agree. I mean, there's some modalities that are super heavily studied, text and images, and there's a lot of other modalities that some companies have done some work on, but that in the end of the day can very much be framed as tabular. So if you think of materials discovery, if you think of RNA folding, protein folding, etc., in the end of the day, the human genome has maybe 50,000 possible features, and these possible features, we can build a tabular foundation model that scales to that. That's not a problem at all. We scaled the number of data points much further. So I think the future is wide open what we can do with tabular, and what has traditionally been attacked with tabular models is just the tip of the iceberg. And actually, even in all of these modalities, XGBoost and CutBoost and so on are already pretty competitive baselines, and we can go much beyond that.
Yeah, I think that's one of the things I've been really impressed by working with you and the team is your focus on delivering stuff that's useful today, right? So if today, and we've got portfolio companies, obviously using Prior Labs, there's some massive S&P 500 companies using Prior Labs, and there's millions of people using the open source version. But if you're focused on delivering value today, if you want to predict that next price move or that next piece of data in your time series, go and try the latest TabPFN model, you'll be amazed. But there's also this incredible range of applications that could be coming down the pipeline. One that I'm really excited by, that I know you've had papers out in Europe's recently about, and we hope will ship at some point soon, is causal inference and what you can do there with tabular data. Could you talk a little bit about what that means, what that leap forward might look like, and how people might use that kind of product in the year to come?
Yeah, absolutely. So in particular, what we had at Europe's was a spotlight that's called datasets. So that is about actually making interventions to your data. You typically don't just want to make predictions in order to predict something. Then you have a prediction, but what are you going to do with it? Really what you want to do with it is actually then intervene, make an action. So you want to make an action, and that action actually changes the statistical nature of your data. So if you have historical observational data, for example, in a medical context, you can think of, well, this patient here had an operation, this patient didn't have an operation, this patient survived this long, this patient survived this long, and you have lots of this data, then you can't just say, aha, this patient here is like this patient, so we're gonna have an operation, because then having an operation, you make this decision, I'm gonna have an operation on this patient, that's an intervention. And what you actually want to reason then with is interventional data. That's why in medicine we do randomized control trials where there isn't a reason that this particular patient had an operation, but then in a randomized control trial, there was an intervention. It's just, flip a coin.
Yeah.
This patient is going to have an operation. This patient is not going to have an operation. And in sort of the causal graph that actually underlies your data, typically, doctors decide based on various features, etc. This patient here should have an operation. This patient shouldn't have an operation. And so there's incoming edges into this decision: should I have an operation or not? And if I have an intervention, then these edges are actually cut, and I just put a value there. And that is something, if you don't deal with this properly, then you get statistical bias. And the only way to actually get unbiased predictions is to have these causal machine learning methods. And in these causal machine learning methods, you want to account for, is this an interventional query or is it not an interventional query? Is this observational data or not observational data? And that is the area that Bernhard Schölkopf, our founding member, is actually world leading in. And so we teamed up and built this datasets, which comes up with this causal machine learning in a really natural fashion. So I can explain this in a tiny bit of detail. Basically, we pre-train our models in order to do this interventional reasoning based on top of observational data. The models are trained with, so the data that we create is created from a causal graph, and we create data from this causal graph once without an intervention, and then again with an intervention. And we use the training data without an intervention to predict the test data with an intervention. And we can do that on a data set that we sampled, we control that, and then we just do this hundreds of millions of times, and so we generate our own training data in order to learn to do interventional reasoning. And once we learn to do interventional reasoning, then you can get some standard observational data and make interventional predictions with this in a learned fashion. And this actually works, and you can't just apply this to the medical field or making decisions about whether someone should get an operation or not, but there's so many decisions you want to make in practice. Like, what should be the price of this product?
Yeah.
For this insurance, what should be the premium so that we actually break even, etc. All of these are interventional questions where you can't just use your observational data and use standard machine learning models. If you use CutBoost, XGBoost, or standard TabPFN, there will be this bias. And if you use proper causal ML methods, that bias is removed. So it's this version of TabPFN with this correction, datasets, that doesn't have that bias, and that then in all of the benchmarks works dramatically better.
Yeah.
So for any internet company that does A/B tests, etc., and has a lot of historical observational data, they definitely need to look at causal ML.
Yeah, and it's, obviously we'll be working on it, and there'll be announcements to be made in the near future about the ability to use this new model. But it's kind of mind-blowing to think that soon you'll be able to do these massive tests of what your interventions can do in silico, as it were, right? Like virtually test whether or not if you made intervention X or Y, what might the outcomes be, when best in class technology companies today, as you say, are running real experiments with real people. Being able to do that in silico, millions of times faster at a millionth of the cost, I think is going to have really huge impact on the way people think about the kind of products they build, whether it's in healthcare, whether it's in finance, whether it's in consumer or elsewhere. So I'm very excited about that in the near future.
Yeah, I'm also super excited about this because I think this can really revolutionize the way that we do A/B tests, for example. I think in 5 years, A/B tests will not be run the way they're currently being run. Right now, there's like thousands of different A/B tests in big systems running in parallel, and you have to question the statistical validity of it, etc. But maybe you don't actually need to have as many A/B tests if you can actually properly do causal ML with observational data. Likewise, randomized control trials. I think in 5 years, they will be run differently because you can actually do this more data efficiently. Randomized control trials also come with some costs, some ethical costs of actually having to give some medicine that you're not quite sure, or not giving a medicine that you think is probably going to help the patient and withholding it. You don't want to have too many of these randomized control trials. And if you can still actually draw solid causal if you can still draw solid causal conclusions, then that makes a lot of sense, and you should be doing that, and you shouldn't be using the standard randomized control trials of the last decade.
Yeah, I mean, producing data, as you say, especially in healthcare, has a huge cost in many different ways. So reducing the data we need is only a good thing. So a lot of your career has been about pushing forward the frontiers of data science in more and more automated ways. Finally then, talk to me, is there a future for data scientists?
I think there is definitely a big future for data scientists. So we need manual checks. Of course, now what we have is this model that makes predictions, and that's typically not where data scientists go and check, okay, like how exactly is my XGBoost making this prediction? There's of course, we have also, we have a lot of extra interpretability layers on top of TabPFN. For example, reshape predictions, they're much smoother than they are with CatBoost, because CatBoost is very axis aligned and makes very sort of has very sharp decision boundaries, and the reshape values that come out are also like jumping all over the place. Whereas with TabPFN, they're much more smooth and much smoother and much more interpretable. But this interpretability is just one thing. It's really about, well, does this data make sense? About like, do these features make sense? The features, we will have also agentic systems that generate features, but we need the data scientists to actually double check this. And the data scientists of the future will be much scarcer, I predict. We had this phenomenon that it was predicted that radiologists will not be needed anymore because computer vision can actually check X-rays so much better. And then not enough radiologists were actually educated, and now there's a shortage of radiologists because actually, guess what? Computer vision systems are really good, but they're not perfect, and they still can't do the outliers and so on. So you need the best radiologists to actually check that everything is going right. So I think we will need less data scientists, but we will need very good data scientists that are trained to use the tools and to double check the tools and to question, is this agentically generated feature here, is this accurate or is this not accurate? So we definitely will need to have people who know that. I do not think that we will need data scientists to look through thousands of different models and tune the hyperparameters, etc. The data scientists that really love to do that might need to look for a different job.
I will take the other side of that bet. I think we'll have more data scientists, But I think, as you say, their job is going to change a lot. And I've worked with lots of data scientists over the years, and that meme is true, where you say doing data science is 90% cleaning data, 9% building the model, and 1% thinking of the experiment, right? And I think what I hope is that thanks to the huge progress you're making and Tabular Foundation models making as a field, as well as explosion of compute and explosion of data, we'll have more and more people who are data scientists who actually get to do the science bit and think up the experiments and think up the tests and use your tools to be even more effective.
Actually, that's very true. Like the science and data science, I love it if people who can actually start to do that, right? Right now, people are stuck tuning the hyperparameters and looking at different models, and not a whole lot of them like that.
Yeah. And look, humans are great innovators. Science is about innovation. I think you're going to help them execute, interpolate, maybe extrapolate. But the innovation bit, I think, will still be human. But everything else below that, I hope, is TabPFN and everything else. So, Frank, thank you so much for making time with us. You and your team executing on the technical and engineering side at a speed I've rarely seen. So I know that you've been very busy in that regard, and we look forward to a huge future for Prior Labs and Tabular Data.
Thank you so much for having me.
Thanks for listening to What's Next. We hope you enjoyed the episode, and if you want to learn more about the frontier of deep technology in Europe today, please like and subscribe. And if you're interested in learning more about working in deep tech, look at the Balderton website to learn more about us and our portfolio companies.